Hello students. Today let us continue our discussion on continuity. In the last class we discussed one of the theorems on continuity, that is, if f and g are continuous functions at a point x equal to c. Okay. F and g are two continuous functions at x equal to c, then we can say that f plus g is continuous, f minus g is continuous, f into g is continuous, and also f divided by g is continuous at x equal to c, provided g of c is not equal to 0. So let me state that theorem again. If f and g are continuous at the point x equal to c, then f plus g, f minus g, f into g, they are all continuous at x equal to c. Then f by g is also continuous at x equal to c, provided the denominator g of c is not equal to 0. Okay, and further I gave a note, that is, if f is continuous at c, then we can say minus f is also continuous at that point, and if f is continuous at c, then 1 by f is also continuous at c, provided f of c is not equal to 0. Okay. So based on these results, let us look at a few problems. First question. Prove that every polynomial function is continuous. Prove that every polynomial function is continuous. Okay. So now let us say what is a polynomial function. A polynomial function, a function p of x is equal to a0 plus a1x plus a2x square plus a3x cube, etc. till an x power n, where an not equal to 0, and all of these a1, a2, a0, a1, a2, a3, etc. till an, they are all real numbers, so I can call it as ai belongs to R. This is a polynomial function. P of x is equal to a0 plus a1x plus a2x square plus a3x cube, etc. till an x power n, where all these coefficients a0, a1, a2, a3, etc., or I can call it as ai, they are all real numbers. An is not equal to 0, that the coefficient of exponent is not equal to 0, then we can say that this is a polynomial of degree n. So this function is called polynomial function. Now we have to prove that this polynomial function is continuous. Okay, so where it is continuous? First let us say what is the domain of this function. The domain of this function is the set of all real numbers. This function is defined for all real values of x. Okay, so now we are asked to prove that this function is continuous, which means we must show that it is continuous at each and every point in its domain. So what is the domain of this function? The domain is the set of all real numbers. So we have to prove that this function is continuous for all real values of x. Okay. So now I cannot take all the real numbers one by one, because it is a never-ending process since there are infinitely many real numbers. So what we do here is we will take an arbitrary real number. Let C be any real number. Let C be any real number. Then we will check whether at this point at C, whether this function p of x is it continuous or not. If it is continuous at C, then we can say that it is continuous everywhere. Okay. So I want to test the continuity of this function at x equal to c. So for that I will go for limit extends to c p of x. That's equal to limit x tends to c, p of x I will write this a0 plus a1x plus a2x square and so on till an x power n. Now if I apply the limit for this function, I am applying the limit as x tends to c, so wherever there is x I have to replace it by c. We will get a0 plus a1c plus a2c square and so on till an c power n. Oh, this is limit x tends to c p of x. Now I would like to find out what is p of c. P of c. Okay. Look here, p of x is defined as a0 plus a1x plus a2x square plus a3x cube and so on till an x power n. We want to find out what is p of c. To get p of c, replace this x by c. So that will give you a0 plus a1c plus a2c square and so on till an c power n. Okay, that is p of c. Now look at this, limit x tends to c p of x. Here we have got a0 plus a1c, a plus a2c square and so on till an c power n. And observe here, in p of c, here also we have got the same thing, a0 plus a1c plus a2c square etc. till an c power n. So from this we can say limit x tends to c p of x is equal to p of c. Limit x tends to c p of x is equal to p of c. What does this suggest? This suggests or this implies that p of x is continuous at x equal to c. P of x is continuous at x equal to c. Okay. So we have proved that p of x is continuous at x equal to c. But the question was to prove that it is a continuous function, prove that the polynomial function is continuous. When I say it is a continuous function, it means it should be continuous at each and every point in its domain. For this function, the domain is the set of all real numbers. So what here we have done is that we have taken a real number. Let's see, be any real number we have taken, and we have proved that at c the function is continuous. Okay. Now, since c is an arbitrary real number, which means c is any real number, this result is true for all real values. So I can, in place of c, I can write any real number. So this result will be true at all those real values. Hence, we can say that the polynomial function is a continuous function. In other words, it is continuous everywhere. I use the word everywhere in the sense that it is continuous at each and every point in its domain. Okay. Let us look at the next question. The next question is, prove that every rational function is continuous. Prove that every rational function is continuous. Now, what is a rational function? A rational function will say, let f of x is equal to p of x divided by q of x. Let f of x equal to p of x by q of x, where p and q are two polynomial functions. P of x is a polynomial function and q of x is another polynomial function. Then p of x by q of x is called a rational function. Now we have to show that this every rational function is continuous. Okay. See here, already in the last example we have proved that every polynomial function is continuous, which means p of x is continuous and q of x is continuous. This is a continuous function, this is a continuous function. So their quotient is also a continuous function. You just recall the previous theorem, that is, if f is continuous and g is continuous, then f by g is also continuous provided g is not equal to 0 at that point. So p of x is continuous, q of x is continuous. Therefore, p of x divided by q of x is continuous wherever the denominator is not equal to 0. So hence, we can say that this f of x is a continuous function. So here, what we need to write is that p is continuous, being a polynomial function, it is continuous. Q is continuous because it is a polynomial function. This is continuous, this is continuous. When f is continuous and g is continuous, then f by g is also continuous, where g of g is not equal to 0. So here also p of x by q of x is a continuous function provided q of x is not equal to 0. Okay. Let's look at the next function. The next question is, discuss the continuity of sine function. Discuss the continuity of sine function. So I will take f of x is equal to sine x. Okay? F of x equal to sine x. We have to discuss the continuity of this function, which means we need to identify where it is continuous, where it is discontinuous. Okay. Already in my first video, I have given, while giving the examples for continuous functions, I have given the example of sine x. There I have told you that it is a continuous function. However, if this question is asked in the examination, then how to solve it, that I will explain now. So f of x equal to sine x we have. The domain is the set of all real numbers, because sine x is defined for all real values of x. So we have to show that this function is continuous on R. Oh. So I want to prove that this is continuous on the set of all real numbers. Now also I will take any real number. I will take an arbitrary real number. Let me say let C be any real number. So it is not that you have to take C only, you can take A, B, D, E, F, whatever you want you can take, other than X of course. Okay, so C be any real number. At the C, I want to know whether this is continuous or not. Okay, so let us say limit extends to C f of x. Limit extends to C f of x. That is equal to limit extends to C sin x. That's equal to limit extends to C sin x. When x approaches C, what happens to sin x? Apply the limit. This will be equal to sin C. Sin C is nothing but f of C. F of x is equal to sin x, therefore f of c is equal to sin c. Therefore, we can write that limit extends to c f of x is equal to f of c. Hence, f of x is continuous at x equal to c. In other words, sin x is continuous at x equal to c. Since c is an arbitrary real number, we can say that sin x, this function, is continuous at all real numbers. Okay. There is another way of solving this problem. I'll explain that also. We have taken f of x equal to sin x and the domain is the set of all real numbers. I will make a substitution, that is, put x is equal to c plus h. Put x is equal to c plus h. Now, as x tends to c, what will happen to h? When x approaches c, put x is equal to c here, C is equal to C plus H, C gets cancelled, H will be equal to 0. When I put X is equal to C, H will be equal to 0. So when I say X approaches C, then this H will approach 0. So as X tends to C, H tends to 0. Okay. So now I want to find out this limit X tends to C f of X, which is equal to limit X tends to C f of X is sin X. Now I am making a substitution as X is equal to C plus H. If I write X is equal to C plus H, I have to change the limit also. Limit as X tends to C, H will tends to 0. So I will write limit H tends to 0. Sin X, in place of X I am writing sin of C plus H. Limit H tends to 0, sin C plus H we have. Here I will use sin A plus B formula, which is a well known formula. Sin A plus B is equal to, yes students, what is the formula for sin A plus B? Yes, you are right, which is sin A cos B plus cos A sin B. So if I use that formula here, I am getting sin C cos H plus cos C sin H. Sin A cos B plus cos A sin B. Now if I apply the limit as H tends to 0, let us see what happens. We get sin C into cos 0 as H tends to 0, this is just 0, plus cos C, that will remain as it is, and this will become sin 0. Okay, cos 0, what is the value of cos 0? 1. 1 into sin C, that will give you sin C, plus cos C into sin 0. Sin 0, it is nothing but 0. So 0 into cos C will give 0. So this is equal to sin C. So what we have proved here is that we have shown that limit X tends to C sin X. See here on LHS we have limit X tends to C f of X. In other words, limit X tends to C sin X is equal to sin C. Therefore, further I will write one more step here. Limit X tends to C f of X is equal to f of C. So f of X is continuous at X equal to C, which means sin X is continuous at X equal to C. Since C is any real number, sin X is continuous for all real values. Okay. After this, we shall look at one more theorem. Suppose f and g, f and g are real valuable functions. Such that f circle g is defined at C. F circle G, in other words, F composition G is defined at C. Then, if G is continuous at C, if G is continuous at C, and if G is continuous at C, and F is continuous F is continuous at G of C. If G is continuous at C and F is continuous at G of C, then F circle G is continuous at C. recall, f and g are two real valued functions such that f circle g is defined at C. If g is continuous at C and f is continuous at g of C, then we can say that f circle g is continuous at C. Now, again, as is the case with most of the theorems, for this theorem also the proof is beyond the scope of your syllabus. So, this proof is not included in your syllabus. However, I will briefly explain what is the meaning of this. F and g are two real valued functions where f circle g is defined at C. G is continuous at C and f is continuous at g of C, then we can say that f circle g is continuous at C. So, see, limit extends to C, f circle g of x, I will take f circle g of x. This is equal to limit extends to C. According to the definition of composite functions, f circle g of x is equal to f of g of x. That's equal to limit extends to C, f of g of x. See here, already it is given that g is continuous at C. G is continuous at C means limit extends to C, g of x is equal to g of C. Then f is continuous at g of C, which meaning is limit extends to C, f of g of x is equal to f of g of C. Okay, limit extends to C, f is continuous at g of C. Okay, so we can say limit extends to C, f of g of x is equal to f of g of C. Okay. So limit extends to C, f of g of x can be written as f of g of C, since g is continuous at C and f is continuous at g of C. So further I can write this as f circle g of C. So limit extends to C, f circle g of x is equal to f circle g of C. So we can say that f circle g is continuous at C. This proof is not necessary. You just need to remember the statement of this theorem. What does this tell you? That is, if f is continuous, g is continuous, then f circle g is continuous. Similarly, if g is continuous and f is continuous, then g circle f is also continuous. Okay. Based on this, let us discuss some problems. Show that the function f of x is equal to sin x square is continuous. Okay. Show that the function f of x is equal to sin x square is a continuous function. Okay. So now I will take let g of x is equal to sin x and h of x is equal to x square. G of x equal to sin x I have taken and h of x is equal to x square. Now look at these two functions separately. Just check whether they are continuous or not. Sin x is a very well-known function. This is continuous everywhere already given. Then h of x is equal to x square. X square is a polynomial function. Okay. See, I said that polynomial function must be in this form: a0 plus a1x plus a2x square, etc. Right? So this is in that form only. I will write 0 plus 0 into x plus 1 into x square plus 0 into x cube, etc. So this is a polynomial function of degree 2. So as we have proved that every polynomial function is continuous. So this function is continuous, this function is continuous. G is continuous as well as H is continuous. If G is continuous and H is continuous, we can say that their composition G circle H is also continuous. G circle H, G circle H of x, that is equal to what? G of H of x, which is equal to G of, in place of H of x, I will write x square. See here, I have defined G of x as sin x, therefore G of x square will be equal to sin x square. Okay, see, now G circle H of x is equal to sin x square. We know that G is continuous and H is continuous, therefore G circle H is also continuous. Okay. So in the previous in the theorem, we have seen that if f is continuous and G is continuous, then f circle G is continuous. Here G is continuous and H is continuous, therefore G circle H is continuous. Okay, let us look at the next problem. Show that the function f of x is equal to modulus of 1 minus x plus mod x. Modulus of 1 minus x plus mod x is a continuous function. Continuous function. Okay. So now here I will take let g of x is equal to mod x and h of x is equal to 1 minus x plus mod x. Okay. First we shall check whether these two functions g and h are they continuous or not. G of x, mod x already we have seen that it is continuous at x equal to 0. Everywhere else it is obvious that it is continuous only. So look at this graph. I can draw this graph without lifting the pen, even though I didn't lift here. Say mod x, this is a continuous function. We have seen at x equal to 0, we have tested the continuity of this function and we have seen that it is continuous at x equal to 0, and at every other points also it is continuous, because everywhere else whenever x is positive it is defined as x, and whenever x is negative it is defined as minus x. Both are polynomial functions and therefore continuous. At 0 also we know that it is continuous. So mod x is continuous everywhere. Then here also this mod x is continuous everywhere. I can treat this as one function and this as the other. This is continuous everywhere we know. And 1 minus x, this is a polynomial function. And we have proved that every polynomial function is continuous. So this is continuous, this is continuous. Then the sum of two continuous functions is also continuous function. Just recall the previous video, there I gave you one theorem. If f is continuous and g is continuous, then f plus g is continuous. So all in all, what we can say is that this g as well as h both are continuous functions. Okay. But the question is to prove that f is continuous, which is this one. G circle h of x I will take. G circle h of x is equal to g of h of x. That's equal to g of h of x. In place of h I will write this, h of x I will write this 1 minus x plus mod x. That's equal to g of this much. G of x is equal to mod x. So g of this factor is equal to modulus of this factor. Modulus of 1 minus x plus mod x. G of x equal to mod x. So g of 1 minus x plus mod x will give you modulus of 1 minus x plus mod x. This is nothing but our f of x. Okay. So here we can say that g is continuous and h is continuous. Therefore, G circle H is also continuous. G circle H is continuous, which means f of x is a continuous function. Students, with that I will stop today's class. We shall discuss and we shall continue our discussion in the next class. Thank you.